Hi there! When creating new circuits that need to be powered up with unusual voltage values or with current generators, using the classic LM317 components is not good enough. For these cases, we need to design more complex circuits using reference voltages and a bunch of transistors and other components. For low-power applications, however, there is also another option that many have used and know already, and that is the LM317 voltage regulator. In this video, I would like to explore this regulator and provide some insight that usually are not well known to the average hobbyist. I will also show you a few practical circuits and how to simply design them without the need of a lot of knowledge on the topic. Let's get into it. The first thing to know about the LM317 is that it is not only a voltage regulator, but also a current regulator. It is also a component very safe to use because it is internally protected against excessive temperature and excessive current. Here is a block diagram that logically describes how the device is internally made. There are just 3 pins for this device, one that takes a DC input voltage, which can be either regulated or unregulated. Then one that is the pin where we extract the regulated voltage or current, and one last pin that takes in input a voltage value used for the internal negative feedback that provides the regulation. Between the input and output pins, we have 2 transistors in a Darlington configuration. The base of the Darlington is connected in 2 separate sources that control its functionality. The one on the left is an op-amp used to provide a feedback through the signal coming from the adjustment pin. Its purpose is to try to maintain an output voltage proportional to the one at the adjustment pin. It does that through a Zener diode of 1.25 volts. The polarization of the diode is kept constant thanks to this current generator, which makes sure that the voltage value between the anode and the cathode of the diode never changes. The other control source that acts on the Darlington comes from this block named Over-Temperature and Overcurrent Protection. In case of overcurrent, this device cuts the voltage provided at the base of the Darlington configuration so that the current will not exceed 1.5 amps. In case instead of over-temperature, the device cuts the voltage again, but in such a way that the whole chip will not exceed the predetermined temperature that would otherwise destroy it. Thanks to this control block, therefore, it is almost impossible to destroy the LM317. This picture instead shows a more detailed view of the inside of the regulator. We can easily see the Darlington configuration here on the right and the more complicated op-amp on the left. Here on the center right instead is the safe net of the device, the one that provides protection against both excessive current and excessive temperature. Let's now take a quick look at the datasheet of the LM317. This one is from Texas Instruments, but of course there are other manufacturers that provide an identical product and their own datasheet. If we look at the features, we notice immediately the operating range of output voltage of the device, which can go continuously between 1.25 volts and 37 volts of output. The 1.25 volts minimum voltage is not surprising, as that is the value of the Zener diode we observed in the block diagram. Note also the current limit of 1.5 amps and the capability of protecting itself from short circuits and overheating. This datasheet provides also a wide range of common applications for the device. Going down through the datasheet, we can see some common parameters of the regulator based on the requested output current indicated in the first column. Particularly interesting is the input voltage range, which needs to be at least 3 volts higher than the requested output, otherwise the device will not be able to regulate the output. Important is also the accuracy, which at the highest currents can degrade up to 1.5% of the nominal value. So, for example, if we arrange the circuit around the regulator to provide an output voltage of 10 volts, the actual output may vary between 9.85 volts and 10.15 volts, depending on the current. Usually, the voltage decreases when the current increases. The LM317 has also a good rejection against ripple, typically introduced in the circuit when the unregulated power supply comes from an AC transformer and a rectifier. The rejection varies with the current, but it never goes below 62 dB. Moving forward, we can see the available packages for the device, ranging from traditional through-hole components to the more recent SMD version. Later on, we have the absolute maximum ratings, where we can see one more time the maximum input voltage of 40 volts, as well as the maximum temperature that the chip can handle, which is around 150 degrees Celsius or 302 Fahrenheit. However, being these the maximum ratings, a more optimal functionality is achieved at the recommended operating conditions, so we should never exceed an input voltage of 37 volts and a maximum temperature of 125 Celsius, even considering the internal protection. And from the temperature perspective, we need to make sure that we add to the component a heat sink of appropriate dimensions, depending on the working conditions of the device. If we don't do so, the internal protections of the device will kick in during normal operations, preventing the device from doing the required regulation, either in voltage or in current. The table of thermal information helps calculating the right size of the heatsink for any dedicated application. In the electrical characteristics, the first two lines tell us that we can actually use the device for both voltage and current regulation, and provides the typical and maximum values of operation. The rest of the datasheet provides information about the typical voltage and current characteristics and transient responses. These allow the designer to better understand how the device can be used. But, fortunately for the hobbyists, later on we will find ready-made circuits for the typical applications of the device, and the very simple formulas to determine the specific values of voltage and current that we require in our projects. So let's now work on a few typical schematics to see how we can use this component. I will mount the circuit on this breadboard, but the problem is that the pins of the LM317 are just a bit larger than they should be to sit comfortable in the breadboard holes. I could actually fit them in with just an extra push, but I don't want to ruin the breadboard contacts by enlarging them by force. So rather than doing that, I decided to build a simple breakout board for the device. To begin with, I installed a heatsink on the LM317. Then I installed the whole thing on a perf board like this. This way, I can use simple pin headers of the right size to connect the regulator to the breadboard. Look at the wires that connect each header with each of the LM317 pins. I also mounted an extra couple of pin headers to sit on the breadboard as a support for the whole breakout board, just to prevent the weight of the heatsink to dislodge the more important headers. At this point, I can just insert the breakout board to the breadboard like this, and go on with all the necessary connections for the rest of the circuit. As a final touch, I added the labels for each of the three headers that connect to the LM317. And here is the basic voltage regulator circuit mounted on the breadboard, with the breakout board for the LM317 and another breadboard I use for powering up the power rails on the breadboard. Here you can see the only two resistors that complete the circuit. The power supply, which I will set to 12 volts, comes in to the V-in pin. The V-out pin is instead connected to a voltmeter, which I will be using to observe the output voltage during the test. At the same time, I have connected the latest version of my DC load between the V-out pin and ground, so that I can load the regulator and see how it behaves. On the left here is visible the power supply that I will use to power the circuit with a 12 volts DC. This multimeter instead is measuring the output voltage of the regulator. I am using this instrument rather than the one on the DC load because those long cables cause a voltage drop, and therefore the DC load voltmeter, instead of measuring the exact output voltage, will measure something less, and increasing the current it will measure even less than it should. The multimeter, taking just a very small fraction of the current, does not suffer of this behavior. In addition, with this setup, I can easily put on the video screen all the information that I need you to see: the output voltage, the input voltage, and the current. Actually, we are seeing this 15 mA even with the DC load disabled, and that is because the power supply is also powering this LED on this breadboard. At this point, we can start our testing. And for that, I will start modifying the current absorbed by the DC load by moving its knob over here. While I do so, we can monitor the three important parameters from here. So right now we have an output voltage of 5.012 volts. Now increasing the current, and while I am now drawing about 117 mA, the output voltage has dropped to 5.009 volts, which is a perfectly reasonable drop considering that we expect a precision of plus minus 1.5%. Increasing now to 250 mA, and the voltage is still well regulated since I am reading now 5.007 volts. Let's increase the current some more. And now we have about 500 mA, and the voltage is still at 5.0 volts. At this point I can feel that the heatsink is a little warm, but we are far away from the conditions where the internal protection will kick in. And in fact, considering the difference of potential of 7 volts between input and output of the regulator and a current of 0.5 amps, the LM317 is dissipating just 3.5 watts. Let's go up a little more. And now we are at 700 mA and the output voltage is at 4.995 volts, well within the 1.5% tolerance. Some more current, and we are still fine. However, since the heatsink I used is not that big, I expect that at some point soon the heat protection will kick in. Let's see if I can get to that point. So we have now a current of 1 amp, but still the output voltage is within specs. In fact, 1.5% drop would mean to go below 4.95 volts, and we are still above that value. However, now touching the heatsink, I can see that it is much hotter than before. Still, I can keep my hand on it without much discomfort, so we are surely still away from the point where the protection will kick in. Trying now to increase the current even further. But you see, now the protection has kicked in because I am not able to increase the current anymore. So let's go down now and disable the DC load. And now let's take a look at the next circuit I wanted to show you. This new circuit is basically identical to the previous one, from the perspective at least of the voltage regulator. We still have the LM317 and the two resistors R1 and R2 that control the output voltage. What has changed in this case is that I added 3 new capacitors. Capacitor C-in to provide some sort of filtering of noise and ripple from the main power supply. Capacitor CO to provide further filtering on the ripple at the highest currents, and capacitor C-adjust, which takes care of eliminating any form of measurable ripple from the adjust pin of the regulator so that the output voltage is well stabilized. The problem is that when we add such capacitors to the circuit, we may incur in some problem when we remove the power supply, due to the discharge of the capacitors over the regulator. To prevent damage on the LM317 in such cases, the datasheet suggests adding a couple of diodes to short the capacitors when they start discharging. These diodes are those that I indicated with the symbols D1 and D2. Besides these enhancements for the removal of residual noise, this circuit works exactly like the one we have already seen in the lab, and so to avoid bothering you, I will not repeat the same experiment. Let's work instead on the next example, which is a constant current generator. This kind of generator uses merely one resistor, R1, which defines the current provided by the LM317 as the ratio between the voltage reference, here rounded to 1.2, and the value of the resistor itself. So, for example, using a 1 ohm resistor, we would have a current of 1.2 amps. Using a resistor of 2 ohms, we would have a current of 600 milliamps, and so forth. This happens because the LM317 will try to keep constant the voltage between the output and the adjust pins, and we know that constant is that known value of 1.25 volt. Basically, when we add a load to this circuit, a current will flow through the resistor R1 and will generate a difference of potential. If this voltage is smaller than 1.25 volt, which means the current is smaller than the ratio of 1.2 and R1, the LM317 will increase the output voltage to compensate, and the current therefore will become higher. On the other hand, if the current is higher than the ratio between 1.2 and R1, we will have a higher voltage between the output and the adjust pins, and the LM317 will compensate by reducing the output voltage, which in turn will reduce the current. So as long as the LM317 can play with the output voltage by increasing or reducing it, the output current will remain constant. But if the circuit will reach the operating limits, either on the upper or the lower end, it won't be able to keep a constant current anymore. In other words, yes, the LM317 can generate a constant current, but only within limited parameters, which of course is also true when it works as a voltage generator. For our lab experiment, we will try to operate in both these conditions to demonstrate the overall functionality of the LM317. So we will calculate the resistor R1 to obtain a constant current of 600 mA, and we will also use a power supply of 8 volt low enough to help us make the LM317 work in both the conditions. We will therefore set the external power supply to 8 volt, and we will use a series resistor R1 of 2 ohm. And here is the circuit I assembled to run the experiment. Note how there is only one single component, this 2 ohm resistor, besides the LM317. The resistor is also able to support a power dissipation of up to 5 watts, which should be more than enough for our purpose. In fact, remember that when a current flows through a resistor, the resistor itself will become warmer, or even hot if it cannot dissipate all the heat produced by the Joule effect. I will also turn on the multimeter that measures the output voltage of the LM317 and the power supply that provides the 8 volts. The moment I will turn on the DC load, we should see the current flowing through the resistor and measured by the ammeter of the power supply. Right now, however, with the DC load off, although the power supply provides 8 volts to the circuit, the output voltage of the regulator is set to 7 volts, and that's because there has to be some difference between the two voltages for the LM317 to work fine. And actually, if you remember, we previously said that there has to be a difference of at least 3 volts for the LM317 to work fine. Since there is no current yet, the regulator tries to output everything it can, which is this 7 volt. As soon as I turn on the DC load, we should see this output voltage decrease below 5 volts, and the current should start flowing. So let's do that. And see, the current immediately reaches the 600 mA we expected, while the output voltage drops to about 2.8 volts. At this point, if I change the load, we should see that the current remains constant, at least for a limited range of load changes. And you can see that this is exactly what happens. However, if I now increase the equivalent resistance of the DC load, at some point the regulator will not have anymore enough voltage range to keep the current constant, and at that point, while the current will start decreasing, the output voltage will reach its maximum value. Let's try that. Increasing the resistance, And here we are, the current is now going down and the output voltage has increased in an unsuccessful attempt to keep the current constant. If we had a greater voltage set on the power supply, the regulator would have been able to keep the constant current for a longer interval of the load resistance. This experiment tells us that if we want to keep a constant current through a large range of load resistances, we need to use a higher input voltage. However, a larger input voltage means also a greater power dissipation on the LM317, and therefore we would need a bigger heatsink to prevent the internal thermal protection from kicking in. Let's now take a look at our last circuit for this video, the schematic for a lab power supply system capable of providing both a variable stable voltage and a variable stable current. The circuit seems to be much more complicated than the previous two. However, if you look carefully, you'll start seeing several commonalities with both the previous circuits. In fact, if you look at the circuit between the point Vin and Vin2, you'll find that to be a current generator, where the value of the current depends on the series of resistor RSC and the resistance between the two upper terminals of the 1K potentiometer. Changing the position of the potentiometer cursor will basically allow us to change the value of the current provided by this power supply. JFET Q1 is used to provide a high resistance toward a -10V reference voltage. This trick allows us to overcome the limit of the 1.25V minimum present between the output voltage and the adjust pin of the first LM317. D1 and D2 help with the polarization of Q1 when the output is open and there is no current flowing into a load. Now, why are we using a JFET instead of an actual resistor? Well, simply because we need a specific behavior of such a resistor with the temperature. A regular resistor would increase its value with an increase in temperature. The JFET does exactly the opposite, which is what we need to compensate the similar drift inside the LM317. Series resistor RSC needs to be calculated based on the maximum current we want this circuit to provide. For example, for a current of 1.5 amps, which is the max current that an LM317 can provide, we will need a value of 0.8 ohm and a power dissipation of at least 2 watts, calculated using the equation from the Joule's effect. The second half of the circuit is now clear. It is a voltage regulator with an output voltage that can be adjusted through this 5K potentiometer. Here, Q2 does a similar job than Q1, but for this second LM317. In particular, in this case, it will allow us to have a range of voltages in the output with a minimum value of 0V instead of that 1.25V value specified in the datasheet. Finally, all the capacitors lying around are there for the only objective of minimizing any possible noise at the output of the whole circuit, and all those capacitors need further diodes to help discharge them when we turn off the circuit. Let's now stop here with this review of the LM317. There is so much more to say about this interesting component, but for one single video I think that is enough. If you have any further question about the LM317, please leave a comment and I will try to give you a timely response. And if I see several answers pointing to the same details, I could definitely make another video to extend this review with those details as well. And just since we are at that moment of the video, I'll just quickly remind you to subscribe to the channel to get notified of new coming videos if you haven't done so already. I'll see you in the next video, and in the meantime, happy experiments!